Good morning and welcome to the 20th lecture. So we have a recitation topic here once again. The main idea here is to reinforce our learning. The first point I have considered is the Shannon-Fano encoding algorithm. So in case of Shannon-Fano encoding algorithm, we will consider a specific example. The example says that a source has multiple symbols being emitted, such as A, B, C, D, E, and F. These symbols, when emitted by the source, they have different probabilities. For example, 0.4, 0.2, 0.2, 0.1, 0.08 and 0.08 respectively for all these different symbols. In this context, we need to find out an encoding scheme using Shannon-Fano encoding algorithm, and also we need to find out the source efficiency and redundancy. What's the amount of redundancy associated with the Shannon-Fano encode algorithm for this specific case? All these factors we need to determine. So first we will see the general steps associated with the Shannon-Fano encoding scheme. So the first step says that when the probabilities are given here, we need to arrange these probabilities in the non-increasing order. So in the next step, what do we do? Once we arrange them in the non-increasing order, we need to group them into two groups. While grouping that there, we need to take care that these groups have almost equal probabilities. So we need to choose the elements in such a way that both the groups, since we are doing two groups, both the groups should have equal distribution of the probabilities, almost equal. And we will assign the one of the groups as a 0, other group as 1. In the third step, we will repeat this grouping process until no further grouping is possible, and that says we have almost reached the end of this encoding scheme. And finally, we will assign the code words, or we will basically track the code words which are assigned in the previous steps. So when we track in the forward direction and collect all the bit sequences, that is the final code word for a specific symbol. So these general steps we will revisit with the help of an example, that's a numerical example. So here are the these are the different probabilities associated with the symbols. And first step, we have arranged them in the non-increasing order. So we have the highest probability here and lowest probability here. And also these are the different symbols. For example, this may be A, B, and so on. So when you arrange their probability, the symbols also get arranged accordingly. That means the symbol and the probability should go together. But in this example, it appears like all the probabilities are already in the sorted order. Otherwise, we need to sort them. Okay, first we sort them and then we divide them into two groups. That is indicated by two blocks here. So the first block consists of two elements, 0.4 and 0.2. So the total probability here is 0.6. In the second group, the total probability is 0.2, 0.1, and again here 0.1. So that becomes 0.4. Okay, so this is 0.6 and this is 0.4. There is no other division possible, better division possible. Either we can group it this way as done here, or another grouping possible is to make a group here. That means 0.4 is in one group and all remaining elements in another group. Then the probability of this group becomes 0.4, and this group consisting of 5 elements becomes 0.6. That is same as the grouping done now. So one group has 0.6, another group has 0.4. If we choose another way of grouping, then the first group will have 0.4 and the second group consisting of all the elements will have 0.6. That's the same. So any way is possible. So this is one of the methods here. So then once we form two groups, one of the groups will be assigned zeros. For example, the top group is assigned zeros and the bottom group is assigned ones. And we will continue this process as per the second step of the Shannon-Fano encoding scheme. So here, since there are two elements, it can be further divided uh, such that each group will have only one element. Similarly, this group has four elements. We can try to divide it further such that the probability should be almost equal in these groups when we divide them. So one possibility is dividing here. So this group will have 0.2 and second group consisting of these three elements which will also have the same probability of 0.2 because 0.1 plus 0.08 plus 0.02 that also becomes 0.2. So that is what shown here in the second step. So one group, I mean a subgroup formed from this bigger group, the first group will have 0.2 this item and the second group will have these three items that are shown here. So even in this case, even this division, we have the distribution of elements having almost equal or exactly equal probabilities here. Okay, so the in this division, that is dividing this group as 2 here, the top element, I mean top group, is assigned a 0 and a bottom group is assigned a 1. So even here there are two groups formed by the division of this group. So the top group is assigned 0 and the bottom group is assigned all ones. Okay, then we shall continue this process. You notice here these groups have only one element. We cannot divide it further. But these groups have multiple elements, so we will divide them further here. So the group consisting of three elements, now we are dividing it into two groups. So the first group will have this element and the second group will have these two elements such that their probabilities in both the groups are equal. Okay, so the top group is assigned a 0 and the bottom group is assigned a 1. Now you notice that only this group can be further divided. We will do that. So when we divide this group into two groups, of course, one element will go to one group, second element will go to second group. This is the best possible division. So the top group is assigned a 0, now the bottom group is assigned a 1. You notice here no further division is possible because every group has only one element. In this context, the algorithm comes to an end. So now we need to pick up the encoded sequences. Let us track those sequences in the forward direction. So for example, the last symbol corresponding to this probability, maybe that is the, so if this is A, B, C, D, E and F, so the symbol F that is here, its code word will be 1 1 1 and 1, and the symbol E will have the code word 1 1 1 and 0 and so on. We can track. Similarly, symbol A will have the code word 0 and 0. This is what is shown here. Symbol A has a code word 0 and 0. Symbol E has a code word 1 1 1 and 0. Symbol F has a code word consisting of all four ones. And the length of code words are mentioned here. For example, here there are 2 bits, so the length is 2. Similarly, here there are 4 bits, the length is 4. So the overall summary here is the code words, I mean the symbols that have a higher probability will have a shorter length code, and the symbols that have lower probability, they don't occur so frequently, then those code words can be assigned a larger code word. I mean those symbols can be assigned a larger code word. This is the idea. Okay, so then we will move forward to find the efficiency. The efficiency is given by this equation, that is entropy divided by the length. So entropy is can be defined with the help of this equation, that is probability and log of 1 by probability. Since we know the probability of every sequence or every symbol that is emitted, we can easily find the entropy. And this length of the code word is basically depends on the probability and the number of uh, bits in a code word, or length of the code word. So for every a symbol, for example, the first symbol having a probability of 0.4 and it has a code word length of 2, there are 2 bits 0 0. So the second symbol, the probability is 0.2 multiplied by the length of the code word, there are 2 bits. So here, similarly, the last symbol F has a probability of 0.02 and its code word length consisting of 4 bits 1111. So we have a number 4 here. That's basically the length of the code word. So we find this value here, the effective length, that's equal to 2.3. So we, since we want to find out the efficiency is nothing but the ratio between the entropy and the code word length, the effective code word length. Since we know these values, we can easily find out the efficiency. Efficiency comes to be the ratio, which is 2.19 and 2.3, 95%. So this is the efficiency of Shannon encoding scheme for this specific example. So since the efficiency is 95%, there is about 5% of wastage or redundancy involved. So that is what we find here, 100 minus efficiency, that gives us the wastage or redundancy involved with this particular uh, coding scheme for this specific example. So this is how we found the encoding scheme. Let us move on to the next concept. So in this case, I have chosen Huffman encoding uh, as, as an example. So in this example, we have different symbols as shown here. There are symbols like A, B, C, D, E, F, G. And these symbols have different probabilities. That's 1 by 3, 1 by 27, and so on here. So now the question is, how do you construct a coding scheme using Huffman encoding and find its efficiency? So to find out this, let us first see how the Huffman encoding scheme operates. So the different steps involved here are the source symbols are listed in the order of decreasing probabilities. The probabilities are given in the question. So first we need to arrange them in the decreasing order. Okay, the next step, two source symbols of the lowest probability we need to pick, and they should be assigned 0 and 1. So since they are already in the decreasing order, it's easy to pick those symbols having the lowest probability. So one of the symbol will be assigned 0, other one will be assigned 1. And in the third step, we need to combine the two lowest probabilities that we have picked in the second step and generate a new symbol. I mean new probability that corresponds to a new symbol. Intermediate symbol, I should say. Okay, so that's the third step, and in the fourth step, the new symbol or the new probability that is generated in the third step, that is placed in the list according to the decreasing order as done in the step 1. So since we are generating a new value here by adding two symbols of the lowest probability, now we need to repeat this process. So while repeating that process, we need to place this new symbol generated in again in the decreasing order. But while decreasing order, we need to see that if there are symbols having the similar probability value, then this new symbol will occupy the first place in the sorted list. Of course, it can be placed at the bottom also, but we will go for placing it at the top of the list. Then we keep repeating this process, that is step 2 and up to step 4. And then once we are done with all the steps, that means no further addition is possible. In that case, our coding scheme gets over, and then we will try to assign the code words, that is, we trace the sequences of zeros and ones assigned to the symbols as well as its successors in the backward direction. So that gives us the code word. So these are the generic steps of Huffman encoding algorithm, but we will see with the help of an algorithm. So already we have chosen our example that there are different probabilities like 0 0.4, 0 0.2, 0 0.2, 0 0.1 and 0 0.2, 0 0.1 as given here. Let us try to see how the Huffman encoding scheme operates. So we have different symbols here, S1 to S5, and we also know their probabilities. We need to arrange them in the decreasing order. So already it's in the sorted order. The 0 0.4 is at the top and 0 0.1 is at the bottom. So the next step is to combine the two probabilities having the lowest value. It's at the bottom of the list. So let us do that. So I have combined here, and one of the symbol will attain a value of 0 and other one will attain a value of 1. Okay, now by combining these two, what do we get? 0 0.1 and 0 0.2, 0 0.1. When we add them, we get 0 0.2. So the new value generated 0 0.2 along with the previous three values here. We need to sort them again. So the list is something like this: 0 0.4, 0 0.2, 0 0.2, and one more 0 0.2 generated here. But this 0 0.2 should occupy the top of the sorted list. That's something like this. So 0 0.4 comes here, and the newly generated 0 0.2 goes to the top of the list, whereas the other two uh, probability values having the same value 0 0.2 will follows like this. Okay, then we will do the same process. We keep repeating the same process. That is, we pick two probabilities having the lowest value and we will combine them. We will assign a 0 to one of the elements and 1 to another element, and then we will combine these two and it becomes 0 0.4. So 0 0.4 is the new element generated. We need to sort it along with the previous list, that is 0 0.4 and 0 0.4, 0 0.2. So the new element generated is 0 0.4. So anyway, this should go to the top of the list like this, and the other elements will follow here. Okay, then we'll continue this process here. We can combine these two having the lowest probabilities. Assign a 0, assign a 1 here. Newly generated value is 0 0.6. The older value here is 0 0.4. We need to sort these two numbers. So of course 0 0.6 should appear at the top of the list and 0 0.4 will appear at the bottom of this sorted list. We have only two elements. Let us combine them. We will assign a 0 here and assign a 1 here. That's the end of this step because we will be reaching a probability of 1 after this. Okay, this is how we perform the Huffman coding scheme. Now we need to determine what will be the encoded scheme for each of these symbols. For instance, we consider S5. S5, how it gets generated. From here, we generate a new value. We go here, and there is an arrow mark that indicates where is the path, 0 0.2 here, and then we go here as well as here and here. Right, this is how we generate S5. So we need to track this path in the reverse direction. So something like this. This is the 0 here, and then I have a 1 here, and then I have a 1 here. So that gives me S5. So 0 1 1 is for S5. Similarly, we can track other elements. For example, S4. Let me see how S4 we can generate. this is the path, and I come here and go here, and then 0.2. From 0.2 I reach here, and then I reach here, and finally to 0.6. Yes, so the reverse path is something like this. I get a 0, and then I get a 1 here, and then I move this direction, and then I move here, and then I get a 0 here. So 0 1 0 is for S4, 0 1 0 is for S4, and for SY it is 0 1 1. That's what we have seen. Similarly, the other code words you can find out by tracking in the reverse direction. Okay, then we will move on to see the other part of this example. So now we need to find out the average code word length, entropy, and variance of average code word length. So first part is average code word length. Average code word length, L prime, refers to the number of bits in the code word multiplied by its probability. The probability of the first symbol is 0.4, and it has 2 bits. Similarly, the probability of second symbol is 0.2, and it has 2 bits, and so on. You just find the summation of these, you get that gets the average code word length. So it says so many bits were used on an average to encode all these 5 symbols. And then we find the entropy. Entropy, we know this with the help of a well-known equation, that is pi log pi with a minus sign, or pi log 1 by pi. There is no minus sign in that case. Okay, now we know the probabilities, so we just keep substituting them and find the sum that gives us the entropy. So basically what we do here is we consider these probabilities and substitute here pi log 1 by pi for the second symbol, 0.2 log 1 by 0.2 here. Similarly, we keep doing that for all the symbols. That gives us the entropy of 2.121. Okay, now the entropy, so some points to remember is the entropy is lower than the average code word length. So this is from the theory, and this should always be observed. So the entropy h of s and the average code word length L prime. So always entropy is less than the average code word length. So this follows this relation. So L prime is the average code word length that is greater, or it can be equal to the entropy, but entropy will never be greater than the average code word length. And now here, zeros and 1 can be assigned in the other way also. That's in this case we have assigned a 0 to the top element, 1 to the bottom element. It can be reversed. Even the combined symbol can be placed below the same probability symbol. That means when we generate a new symbol, we place it at the top of the list, sorted list. That could be placed at the bottom also. What happens if we do that? The code words may differ, their length also may differ, but the average code word length, that is EL prime, that remains the same. So that's the significance of this particular algorithm. Okay, now the third part in the question is to measure the variance of the code word length. So variance is determined by this equation, that is probability of the symbol multiplied by the length, that number of bits used in the particular code, minus the average code word length, its square. So for example, the first symbol, the probability is 0.4. It had 2 bits in its symbol, so we have a number 2 here, minus the average code word length that we determined in the previous step is 0.2. Similarly, for the second symbol, its probability is 0.2. Its code word size is also 2. There were 2 bits in its code word, and average code word length remains the same in all these, that is 2.2. And yeah, we substitute them here for every case and find out the variance by substituting in this equation for every symbol k. Okay, this gives us the variance. Now we will check if we place the combined sequence at the bottom of the list, what would happen? Or if we assign it different way, that is the top symbol is 1 or bottom symbol is 0, then what would happen? We will see one of these cases. For instance, we consider the same example, and now we combine two symbols and assign a 0 here, 1 here. There is no change, but we will place the newly generated symbol at the bottom of the list here. In the earlier case, we had placed it at the top of the list. Now we will be placing it at the bottom of the list. Okay. Now the next step is to combine these two symbols and generate a new symbol, that is 0.4. So 0.4 will be placed here. In the previous case, we had placed it here at the top of the list. Now 0.4 is placed here because this 0 point place will be placed at the top, and this 0.2 is placed here. Okay, and again we have to combine these two symbols and generate a new symbol. So that is 0 and 1, and the newly placed symbol 0.6, of course it will go to the top of the list because that is the uh, highest probability value, and it will come to the bottom. So there is no doubt here, but in this case, if you see this step, since this new generated value is 0.4, the older value is also 0.4. So when we sort them, there are two options, either placing at the top of the list or at the bottom of the list. So in this particular case, we have placed it at the bottom. So in the earlier steps, earlier example, we had placed it at the top of the list. So we are investigating here the second case. What happens if we place it at the bottom of the list here or the bottom of the list here? Okay, then continue the same process and we get the symbol here. So again, to know the code words, we need to do the backtracking as done earlier. So if you do the backtracking, you will come to know what would be the code words. So these are the different code words that we generate. So if we compare here, the average code word length in this case, probability multiplied by number of bits in for every symbol, average code word length is 2.2, and the variance here, that is pk multiplied by lk minus l prime whole square, that is for the first symbol probability is 0.4, the number of bits in the first symbol is just 1 minus 2.2, the average code word length remains the same, that is what we have seen in the theory. So the average code word length remains the same no matter you place it at the top of the list or bottom of the list. But when you find the variance values so much. So we have seen both the methods, placing the newly generated symbol at the top of the list or bottom of the list. What happens here? They should move the combined symbol up to get the minimum variance. So in this case, we kept the newly generated symbol at the bottom of the list. So variance is 1.36. In the earlier example, we had placed the newly generated symbol at the top of the list, then the variance was much lesser than this, around 1.02, so on. So the takeaway here is wherever you place the newly generated symbol, no matter when you consider the average code word length, the average code word length remains the same, but the variance will increase. So it is to get a lower variance, which is generally preferred, we need to have the newly generated symbol at the top of the list as done in the first part of this example. Okay, so now we need to remember that the coding efficiency is computed by this equation, that is entropy divided by the average code word length, and the redundancy is computed by this equation. Yes. So now in the next example, which of the following code words are a prefix free? That is instantaneous codes that we need to find out. So first one, we need to draw the tree diagram in the next case. So first one, there are four code words given. We need to find out which of them is prefix free. Prefix free means one sequence is not the prefix of any other sequence as given here. So in that case, it is called as prefix code. Prefix free codes are easily decoded without any confusion. If a code becomes a prefix of another one, then it cannot be uniquely decoded. So let us see which of them are prefix free. So let us see code A. There are some symbols given here and they are encoded bits. So 0 here, the first one. Is there any 0 here beginning with 0? No. 1 0. Any other have a 1 0 here? Okay, it looks like no. Next 1 1 0. Anyone has a 1 1 0 here? 1 1 0. So we have a 1 1 0 here. Okay, then 1 1 1 0. Anyone has a 1 triple 1? Yes. So let us see here. There is 1 1 1 here, and this code word also has a 1 1 and 1. So when you see this particular code word, there is a confusion that whether this code word consists of this as well as this, or is it a unique code word? It's difficult to identify, right? So suppose I give you a code something like 1110, then from this list, can you say whether this is a specific symbol, or maybe it's also possible that you can say that this is a combination of this symbol and this symbol. 111 refers to this code and that 0 refers to this code. So whether it's this particular symbol, maybe symbol 4, or is it symbol 5 and symbol 1 together? So there is a confusion. It is not unique. So this entire code A is not prefix free because there is a prefix here which is another code in its entirety. Okay, now we'll go to see the second one, that is code B. So in case of code B, is there any such instance? So 1, there is a 1 here and 1 0 here. Okay, next 0 1, anywhere 0 1 here? No. Okay, next triple 1 is not present in anyone here. 1 0 is not okay. 1 0 consists of a 1 from this one here. So again, it's a confusion, that is whether this 1 is from here or this 1 0 is entirely a different code word. So 0 0 is not here, anywhere here. So because of this 1 and 1 0 here, so again there is a confusion here. There is a 1 here and 1 1 here. So whether this one corresponds to this. So basically this one, the entire code word present here as well as here, right? So there is a confusion here whether this is something unique or it's a combination of this and something else. So again, B is not a prefix free. Let us see C. In case of C, is there any such instance? See here, there is a 0 0 here and there is a 0 0 here. So that gives us a, I mean, it is not easy to decode whether this is a new symbol or this is a combination of this as well as something else. So again, this is not a unique code word. Now we see here D, it has 1 0 here, there is no 1 0. Triple 1 here, there is no triple 1. 0 1 0 0. So there are no prefixed code words. So this sequence D is a prefix free code word because none of these sequences have any other sequence completely present. No. For example, here if you see there is 0 0 and 0 0 totally present here. If you see here, this is 1, there is 1 totally present here, 1 totally present here. Similarly the case of A. But here 1 0, there is nowhere 1 0. 0 1, there is nowhere 0 1. 0 0, there is nowhere, no sequence is starting with 0 0. So that's why this code sequence D is prefix free. So if it is prefix free, then it can be easily decodable. So let us write it in the form of a tree diagram. So we start the tree with a root node, and then on the left hand side we will name it as 0, on the right hand side we will name it as 1. And then here again on the left hand side we will write it as 0, and right hand side that it becomes 1. So now we will try to decode 0 0. 0 0 corresponds to which symbol from the previous list? That is symbol 4, the last symbol. And next 0 1 corresponds to which symbol? The S3 from the previous list. Okay, now we will continue writing the tree diagram. This is basically written based on what symbol we had earlier. For example, here when you see D, the last symbol S4, S3, S2, S1 and S0, the last symbol's code was 0 0. Before that 0 1. How to write that in the tree? That's what we are doing here in the tree diagram. 0 0 corresponds to S4 and 0 1 that corresponds to S3. Similarly 1 0 that corresponds to S0. 1 1, if you look back, that corresponds to nothing. So we need to continue the tree. 0 1, always on the left hand side we have a 0, on the right hand side we have a 1. So 0, so now if you see 1 1 0, that corresponds to S2, and 1 1 1 that corresponds to S1. Is it so? We can go back and check. So let us just see these two. S1 is 111 and S2 is 110. So I just go back to see the diagram here. So S1 is 1 1 and 1, S2 is 1 1 and 0. That is what written in this tree diagram. So once you know the code, you just need to write the tree. When you write the tree, every branch will have on the left hand side 0, on the right hand side 1, on the left hand side 0, right hand side 1. Similarly here, the left hand side 0, right hand side 1. So how long you need to continue? That is based on how many bits you have in the symbol. I mean, the encoded bit pattern will decide how long the tree should be. In this case, since the S1 is just 1 1 1, we can stop at this point. Okay, and next we have the Shannon's first encoding theorem. So we know the general steps of Shannon's encoding theorem. First, we need to arrange the probabilities in the non-increasing order, and then we need to compute the length of the code word for every symbol. So the length of the code word for every symbol I, that should be at least, mean greater than or equal to the log of 1 by probability. Since we know the probability, we can compute this value, and we need to choose this Li greater than or equal to this value. And then in the third step, we find out some parameters. So parameters are found in this way. For example, the first parameter Q1, what we denote it as, will have a value of 0. The second parameter will have a value which is nothing but the probability of the first symbol. And the next parameter Q3 is the sum of the previous two symbols probabilities, and it continues in the same way. For example, if you consider Q4 here, Q4, it's a sum of probability 1, probability 2 and probability 3, and so on. It continues up to n plus 1 symbol, and that will have the sum of all the previous symbols. So when you consider all the probabilities, that is 1. Okay, in the fourth step, we expand these q values in binary. How many bits we need to have when you write represent that in binary? It should have li number of bits. From where the li comes from? Li comes from the second step. So many bits we need to have after the decimal point. And finally, the bits placed after the decimal point are the code words. So we will see these general steps, how it goes into a specific example. So here we have the example. There are four symbols A, B, C, D, and their probabilities are 0 0.1, 0 0.2, 0 0.3, and 0 0.4. Now we need to encode these symbols as we know their probabilities using Shannon's algorithm and find the source efficiency and redundancy. So basically we need to apply the Shannon's encoding algorithm that we have seen in the previous slide here. So the first step is to arrange the probabilities in the non-increasing order. So that goes something like this. So when we arrange the probabilities, their symbols also correspondingly sorted. Okay, the second step is to find out Li. Since we know the probabilities, we can easily find these values. For instance, for the first symbol, the probability is 1 by pi, that is log of 1 by 0 0.4. That gives us a value of 1.32. So this relation says that Li, that is L1, should be greater than or equal to 1 by 32. So a number which is greater than 1.32, whole number is 2. So Li value is 2. If it is already a whole number, then that number can be applied here. Okay, for L2, the value comes to be 2. So for L3, the value comes to be 2.31. So that can be equated to 3, the next higher value. Similarly for L4. Okay, in the next step, in the third step, we need to find out some parameters that are Q parameters. So the first value Q1 is always 0. The second value Q2 is produced by the first probability 0 0.4. The next value is produced by adding two probabilities, that is 0 0.4 and 0 0.3. Two probabilities are added here. And the next value is added by adding three probabilities 0 0.4, 0 0.3, and 0 0.2. Yes, that is 0 0.9. The next one is of course 0 0.4, 0 0.3, 0 0.2, and 0 0.1. That gives us the value of 1. So that's the final step. So we have all these Q parameters ready now. So in the next step, we need to convert these values into binary. While converting that, we need to take care that the binary converted sequence will have Li number of bits in the decimal point. I mean, after the dot, we will have so many bits. For example, when we convert this into binary, it should have at least two digits after the binary point. Similarly, here we will have four digits after the binary point. Okay, that's what we are doing here. For the first one, its value is 0 in decimal. When we convert it into binary, that's also 0.00. Since the code word length is 2 for the first symbol, we have 2 bits here. Okay, so the next value Q2 is 0 0.4 in decimal. It is base 10, not multiply by 10. So 0 0.4 in decimal value. So this one, when it converted into binary, it becomes 0.01. So we need 2 bits here. So we have stopped at this level 0.01 because its length is only 2 bits. So 01 becomes the code word. 01 is here, so that becomes a code word for this particular symbol. Okay, then we have similarly for Q3, we have the value 0.7, and when we convert it into binary, it becomes 0.101. We have only three digits here because its size is 3 bits. In the previous slide, if you go back and see, the length is 3 bits. So we have 101, these bits, they are the code words for this particular symbol B. Similarly for Q4, the value decimal is 0.9. When it is converted into binary, it becomes 0.1110. There are 4 digits here because its code word length LI is 4, and these 4 bits forms the code word for symbol A. Now the important takeaway here is the message with the highest probability will have the shortest code word length, and vice versa. This we have seen even earlier. And all code words are unique, and they can be easily identified, and they are easily decodable. Now to find the efficiency, the equation is entropy divided by L, average code word length, multiplied by 100. So probability log of 1 by probability for every symbol. When you sum it up, it gives us an entropy of 1.846. Then the average code word length is nothing but the probability multiplied by number of bits in the code word for every symbol here. When we sum up this, it gives us 2.4. Now it's easy to find the efficiency by the ratio of entropy and average code word length. That gives us an efficiency of 76%. So the redundancy is nothing but 100 minus this value, that's around 23%. So that's the end of this example, and also this is the end of this lecture here.